We'll see on Kirchhoff's law. Kirchhoff's law is one of the most interesting law which defines how the current is passed at a junction and what could be the value. So this is the index we are going to see now. That's Kirchhoff's law. The first law, second law, followed by the Wheatstone bridge, meter bridge, and determination of specific resistance and determination of temperature coefficient of resistance. Now we'll see on Kirchhoff's law. So Ohm's law is applicable only for simple circuits. For most complicated circuits, we'll be going with the Kirchhoff's law to find the current and also the voltage. There are two generalized laws. One is Kirchhoff's current law, the other one is Kirchhoff's voltage law. So what is that Kirchhoff's first law? So Kirchhoff's current law states that the algebraic sum of the current meeting at any junction in a circuit is 0. You can see I1 which is coming inside, I2 which is going outside, so minus I2. I3 is going out, it's minus I3. I4 is going towards, so I4 plus I4, and I5 is going towards, it's plus I5. So the combination of or sum of all the current at a particular junction O is considered as 0. The convention is that the current flowing towards a junction is positive and the current flowing away from the junction is considered as negative. So let 1, 2, 3, 4 and 5 be the conductors meeting at a junction O in an electrical circuit. And I1, I2, I3 and I4 and I5 will be the current passing through the conductors respectively. So on applying the Kirchhoff's law, first law, will be getting I1 minus I2 minus I3, I4 and I5 is equal to 0. So minus will become plus here. So minus will come plus here. Minus will become plus here. We'll be getting the equation I1, I4 and I5 is equal to I2 and I3. So Kirchhoff's first law can be redefined as the sum of the current passing towards the junction is equal to the sum of the current which is passing away from the junction. This law is a consequence of conservation of charges. Now we'll talk about the Kirchhoff's second law in a closed circuit. Kirchhoff's voltage law states that the algebraic sum of the product of the resistance and current in each part of any closed circuit is equal to the algebraic sum of the EMFs in the closed circuit. This law is a consequence of conservation of energy. In applying Kirchhoff's law to electrical networks, the direction of current flow may be assumed either clockwise or it can be anti-clockwise. If the assumed direction of the current is not the actual direction, then on solving the problem, the current will be found to have negative sign. If the result is positive, the assumed direction is the same as actual direction. Good. Further moving, this is your closed circuit. So this is how we are going to take it. If it is in the clockwise direction, we'll consider it as positive. If it is anti-clockwise direction, opposite direction, then it's considered as negative. Let us consider the closed loop electrical circuit A, B, C, D, E, F, A. Let's take on the closed circuit of ABCD EFA. We'll get through Kirchhoff's second law I1 into R2 plus I3 into R4 plus I3 into small r3 plus I3 into R5 plus I4 into R6 plus I1 into R1 plus I1 into R1 is equal to the total electricity is given from E1 and also through E3, which is given here. This is your Kirchhoff's second law. The algebraic sum of the product of the current and the resistance in a closed circuit is equal to the power given to the circuit. Both E1 and E3 send current in clockwise direction. Let's move on to another closed loop A, B, E, F, A. So I1 R2 plus I2 R3 plus I2 R2 plus I4 R6 plus I1 R1 plus I1 R1, which is equivalent to E1 and E2. Since the direction of current is in the, you are able to see the positive here. It's in the opposite direction, we got the negative sign here. It indicates E2 is sending the current in the anti-clockwise direction.